Hello everyone, I am Grammy from class 11-4.
I am Zisel from 11.6.
I'm Darren from 11.7.
In this video, we'll be talking about our centripetal force experimentation. The experiment itself has two objectives. Firstly, to determine gravity acceleration through centripetal force experimentation, and secondly, to validate the formulation of centripetal force. First of all, to start off, we would like to state about Newton's second law, which states that the force applied on an object is equal to its mass multiplied by its acceleration, which is pretty basic stuff. When something's cruising in a circle at a steady speed, the force and acceleration act sideways according to its speed, or, well, more precisely, velocity, because it definitely has a direction. They both pull towards the circle center from where the object is, and the whole loop around measures 2 pi radians. So we can switch from the time it takes to go around and how fast it's spinning, which is equal to 2 pi divided by the time it takes. And this spinning speed also in the, in radians per second is like how fast things zip around when they're not going in circles. The spinning direction is at a right angle to the spinning plane. To find how fast the velocity is going, you can use the formula of velocity equal to 2 pi times the radius of the circle itself divided by the time taken. And for acceleration, it can be using a formula of acceleration equals velocity squared per radius. Using Newton's second law, it's possible to work out the force pulling in, or let's say, for example, we put a variable fc as fc equals mass times acceleration, or, well, to be more precise, fc equals mass times 2 pi r divided by r squared. And that would, if we were to continue on with that, it would create 4 pi square times mass times radius divides by the radius square. Within the experiment, there were multiple apparatus that we use. Some of them include a plastic tube or pipe with small diameter, loads with different masses, a string with one end attached to a stopper, which will be used to create a circular motion, a ruler to measure the radius of the string moving in a circular path, a marker to mark the radius so it would be constant every repetition, a triple beam balance to measure the mass of the loads, and finally a stopwatch to measure the time of the number of revolutions. To conduct the experiment, we began by marking the string to ensure a constant radius for the circular path. We marked 31.5 centimeters for the stopper, and we must also, during the time of the experiment, determine the mass of the stopper, which registers at 32.5 grams. These serve as our control variables. X, we measure the mass of each load, which serves as our independent variable. We establish 5 variations of loads, which are 68.5 grams, 92 grams, 93.6 grams, 114 grams, and 135.2 grams. To initiate the circular motion, insert one end of string into a pipe and affix a load to its opposite end. Holding the pipe vertically, execute a circular wrist motion to induce horizontal movement along the string. Adjust the string's radius to match our predetermined mark. Once the motion achieves stability and uniformity, record the duration of one complete cycle, and that becomes our dependent variable. This procedure should be repeated for each load variation. So, the experiment's data is summarized below. Throughout the experiment, the radius r and mass of the stopper remain constant at 31.5 centimeters and 32.5 grams respectively. With a load of mass of 68.5 grams, the period time was 0.61 seconds with 92 grams. It decreased to 0.59 seconds with 93.6 grams. It further reduced to 0.56 seconds with 114 grams. It dropped to 0.49 seconds, and with 135.2 grams, it reached 0.43 seconds. These results demonstrate a clear trend. As the load masses increase, the period increases. We converted our data into a graph as follows. Keep in mind that the primary aim of this experiment is to determine gravitational acceleration. To achieve this, we applied the formula gravity equals to the stopper's mass times by 4 pi per square divided by the average period squared, times by the radius of the circle, divided by the average m value. Using the average values of m and the period, the calculated average m value seems to be 100.66 grams, and the average period value is 0.536 seconds. Putting these values into the formula yields a gravitational acceleration value of 13.98 meters per second square. Referring to the currently accepted gravitational acceleration value of the Earth, which is 9.81 meter per second square, the experiment yielded a percentage error of 42.5%, calculated as the percentage error is as follows. This wide deviation indicates significant inaccuracies. Potential error sources include human errors in period determination and inconsistent wrist motion. To enhance accuracy, future iterations should prioritize precision as well as accuracy and care during experimentation, alongside upgrading equipment to better illustrate centripetal force. To summarize the whole explanation, the experiment effectively demonstrates the determination of gravitational acceleration of the Earth through centripetal force. Consequently, it validates the formulation of centripetal force itself. Nonetheless, it is not an accurate representation, and I do hope that future iterations, or maybe even repetitions, can help increase the accuracy of these results. I am Grammy, and I am the presenter for the experiment for Class 11B of Physics of Sir Martin's class, and I do as a representative of Group 6. And I hope you enjoyed this video.